Hello, 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 hello. All right. I hope my stomach hurts for some reason. I hope you can hear me. It's been a while since I did one of these. I hope anyone who watches this now or in the future is doing well. Trying to be the best person that they can be. Um, guess that's what we can. That's what we should hope for, right? All right. Without much that needs to be said, I just wanted to drop by and do a watch along or like code along and learn along of Neel Nandas, who is a leader at Anthropic, or no, is it Anthropic or Google Mind? Let's see. Oh yeah, Google DeepMind's mechanistic interpretability team. So he leads that. In general, I found him a very clear communicator, and I saw that he had some lectures. Yeah, I saw that he had some lectures. No, sorry, a lecture series of like mainly two, right? Like he says, part one of two, but he also added a third longer lecture that I guess describes a bit more about his day-to-day job, which is like the mechanistic interpretability. Right. Let's see if I can get the zoom in. All right. Hopefully you can see it better. All right. So what I wanted to do was just watch him go through it and try to understand it alongside. And so he has a template notebook that he has shared here that I'll also keep to my side. Let's see, move to new window. All right, and go here, and where's that? Go here, and go here. All right. Oh, I can't see it. Let me stop sharing this and share the entire screen. Yeah. Also share the sound so that his beautiful voice, Neel Nanda's beautiful voice, comes through for people that might be following alongside. Okay, all right. Hopefully it is legible. So this is the template that he shared. Oh, this is GPT-2 template. Let's see part here. That's interesting. So does he not have? Oh, he does have. So this is the tokenization thing. But yeah,
Is that
we'll know. Yeah, let's listen to him. Hey, what?
at the end of this two-part video series, you'll leave with a pretty deep intuition for what is a transformer and how does it work. Before we jump in, I want to give some context on why I'm making this tutorial and what I think it can add that the other excellent existing tutorials don't. I'm a researcher of mechanistic interpretability of language models. I try to open up the black box of models like GPT-3 and reverse engineer what algorithms it's learned and what's going on internally. I think this is just like a really fun thing to do, but I also think it's just a really important question. We just live in a world where we have computer programs that can speak English at a human level.
Sorry, I'll just speed him up a little bit.
And we have no idea how they work, and this is terrible. In order to just use a model, you don't really need to fully understand how it works. But if you want to open it up and look at its internals, you really want an extremely deep and thorough understanding of what is going on and how the different parts of it work and fit together. My hope is that by the end of this two-part series, you'll have written the code for a transformer yourself from scratch and left with a deep understanding of how it works and what's going on inside of it. If you find this fun and want to continue exploring what's going on inside these models, I think mechanistic interpretability is a really exciting field. and has lots of low-hanging fruit, and I would love to see more people get into it. In the description, I'll link to a sequence I've written called 200 Concrete Open Problems in Mechanistic Interpretability. This sequence has advice on how to skill up and learn more about the field, tooling that I've written. I have a library called Transformer Lens that makes it easy to poke around inside models like GPT-2, and a long list of 200 open problems that people new to the field, I think, could realistically work on and try to contribute. Great, so this is part one of a two-part series. In this part, I try to convey conceptually what is a transformer. What are the moving parts inside of it? Why do transformers exist? What do they do? This is mostly me talking and a little bit of me writing code. The goal is to be a fairly gentle, accessible introduction aimed at people who just never heard of a transformer before, but maybe vaguely know what a classic neural network is. In part two, I code GPT-2 from scratch, talk through what I'm doing, and give a template notebook for you to do this yourself. And I begin that with a brief recap of what I cover here. So if you find this too slow, or you feel like you kind of get what a transformer is and what a tension is, but just want to see how everything fits together, I recommend skipping to part two. But if not, I hope you enjoy this journey through what is a recap of what I cover here. So if you find this too slow, or you feel like you kind of get what a transformer is and what a tension is, but just want to see how everything fits together, I recommend skipping to part two. But if not, I hope you enjoy this journey through what is a transformer. I am going to be coding up a tutorial as I do this, which will also involve me writing some notes and writing code and generally trying to create a thing that someone could look at to accompany this video. And I highly encourage you to go play around with this yourself and try to implement something as well. I think it's really easy to watch a video, think you kind of understand things, and like not really, but not actually test your empirical knowledge so you don't notice this. And getting your hands dirty and doing shit is one of the best ways to solve that. But yeah, let's jump in. This is some pretty boring setup stuff. This is an incredibly hacky block of code that says, try importing a module that's only there if you're in Colab. If yes, you're in Colab. If it's a done error, you're not in Colab. And install some libraries. Here, I'm actually importing some of the various libraries. Respectively, Inops is a beautiful library for manipulating tensors and lets you just take any tensor, do basically anything you want to manipulate that tensor, like moving shapes around, moving the tensor elements around, repeating the tensor, so like copying the elements along some dimensions, reshaping it in weird ways, taking the average across some dimensions. Generally, Inops is just amazing, and I'm going to write this whole thing in Inops. Fancy Einsum is a library designed by Chris McLeod at Redwood that I love, and is basically Einsum, which is like part of Torch and NumPy, and it's kind of a generalized thing that you can use to take in a bunch of tensors and do a kind of generalized matrix multiplication on them. This is kind of hard to explain in the abstract, but I'll hopefully be clearer when we get to it. Fancy Einsum lets you give things nice named axes. It's beautiful. Data class is a random Python utility for writing nice config objects, not super important. And these are two things from my interpretability library. Easy Transformer is the main class for defining a transformer. Hook points are some utilities we're going to be using to get out activations from within a model. Actually, on reflection, we can kind of skip the hook point stuff. The important point is get a clean idea of how the transformer works. And you can go and use the hooks with an easy transformer to figure this out on your own. Let's import those. These easy transformer.from pretrained just loads in an open source model. Here I'm going to load in GPT-2 XL, which is a million-sized model for when I want to demonstrate what a big chunky model looks like. And for the most part, I'm going to keep around this reference of GPT-2 small, which is a 80-ish million parameter transformer. As we write our transformer, we're going to be checking how it actually works and using this reference transformer to validate things. Let's jump into this. I think that before we really get into the guts of how a transformer works, it's worth getting a crisp understanding in your head of what is a transformer trying to do from the perspective of being a black box. So let's make a section called Understanding Inputs and Outputs of a Transformer. This is definitely not sufficient to like reverse engineer it, but in general, the way I think about ML models is they're designed to take in some input format and return some output format. ML models are really fucking good at dealing with the vectors and really bad at dealing with anything else. So you want to first understand the like high-level task they're being trained to do, then you want to understand how we convert that to vectors, and then you want to understand like exactly what the vectors mean. That splits into a few sections. What is the point of a transformer? What are the inputs to a transformer, which are these fucked up thing called tokens, and what is the output, which is these things called logics. And yeah, so why do transformers exist? Transformers exist to model text. We're going to focus on GPT-2 style transformers. There's like lots of random shit about different kinds of transformers, but in my opinion, GPT-2 or GPT-3 style transformers are like the main game in town nowadays, and the main thing that's actually interesting. The key feature is that they generate text. You feed in language, and the model generates a probability distribution over the next tokens, and you can repeatedly sample from this. The way the model is trained, which is always a like important thing to keep in mind, we're trying to understand what a model is and how it works, is you give it a bunch of text and train it to predict the next token. I'll get to it a bit later, but token basically means subword. And this is a kind of janky fucked thing about how transformers work. And a really important thing to note, if you give a model 100 tokens in a sequence, it predicts the next token for each prefix of that sequence, i.e., it produces 100 predictions. It's like not intuitive that this happens. Like, in some sense, the only thing you care about if you give the model 100 tokens is what thing's going to come after the 100th token. But it turns out that it's just much easier to structure a transformer to do this. And hopefully by the end of this, you'll have an intuition for why. And it also makes training more efficient because if you have 100 predictions, you can get 100 bits of feedback rather than just one. A natural objection would be you're training the model to predict the next token. You give it 100 tokens, it makes 100 predictions, but like 99 are trivial because you've already told it what the next tokens are, so like what? And the reason it's not trivial is we make the transformer have causal attention. I'll get to exactly what this means later, but the core thing is that it can only move information forwards. The prediction of what comes after token 50 is only a function of the first 50 tokens, not of token 51. And we will later see exactly how this works. So drawing this out, a really key takeaway of transformers in general is transformers are sequence modeling engines. The thing you are fundamentally trying to do when you train a transformer is give it a sequence and have it do some weird shit with that sequence. This is like a pretty deep and important thing to get your head around when looking at the internal structure of the transformer, because the like core thing it's doing is that it's basically doing the same processing with the same parameters on every point in the sequence, and then it's using a mechanism called attention to move information between sequence positions. But like in theory, a transformer should just be able to take in a sequence of kind of arbitrary length. Drawing that out, it does the same processing in parallel at each sequence position, can move information between position and attention, and conceptually can take a sequence of arbitrary length, brackets not actually true, see you later, because things are messy. But yeah, that is the point of a transform. It takes in text, it predicts the next token in this auto-regressive way. Auto-regressive is jargon for causal. Things can only look backwards and go forwards. The other meaning of auto-regressive is that the transformer's output is then used as its input. Like, you can generate text by just repeatedly having the model predict the next token, sample from that, and continue. But yeah, that is the point of a transformer. This is just like a pretty important thing to get straight in your head. So if you don't really follow that, you should pause the video and just make sure you really get it. Because if you don't understand why a model exists, you are not going to properly get your head around like how it works and what the point is. Fundamentally, the core point of the input of a transformer is language, i.e. a sequence of characters, I guess, strings, etc. For models like GPT-3, you can give it inputs of something like up to 1,000 to 2,000 words. They can take in like pretty long.
Yeah. Let's see. Start again. Reconnect. I think since it has been a while between this lecture and when he created this, there must have been like some version changes that is breaking this up. So let me see though. Gemini found a solution of some kind, or at least it thinks it has. So let's see if that works. In the meantime, let me just try to summarize for myself what Neel explicated so wonderfully, which is right, what a transformer is. Right? A transformer is a neural network model, or a deep neural network model, where you feed in something, which are like the inputs, right? Like we haven't clearly defined what the inputs are right now, but we'll do that. And then you get certain outputs. Let's say. Now, what are the inputs? The inputs are language, right? More carefully or more accurately, it's tokens that are approximately, like in terms of length, 3 or 4 of generic words. So for example, why is it not? Oh. So for example, it can be like this. I don't know if it's truly right. If we have a sentence like a cat sat on a mat, full stop, there might be, it might get broken up into a comma cat, a comma space comma cat comma space comma dash 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 dash, right? So these, and this process is known as tokenization, right? There are many, we are not really studying this in detail right now. It's not particularly interesting from a fundamental perspective. And like, there are algorithms that that enable us to do this tokenization more effectively. One of the algorithm is to produce such a tokenizer is called byte pair encoding, where, if I remember correctly, and if I had understood it correctly, it is like you go through the vocabulary of, you go through all the words that appear in your training data, so to say, and then try to understand like what are given a constraint, which can be something like, oh, I want, yeah, given a constraint, like I want n number of tokens from my language. Why is this? Sorry, just frustrated with this. Huh. It's pretty interesting. Or maybe I wrote too much. Let's see if I can. Okay. So let me just write tokens here. This is, well, might as well write it with hands, right? So let's try to understand. Is given a constraint, like I want n number of tokens from a language, what the algorithm does is the algorithm finds out the n most common / repeating blocks and considers them as tokens. For example, we know that something like broken, right? Something like, in a word like broken, the n, like this, can repeat over broken, swollen, right? Like, so this en as a pair of characters will repeat significantly, such that like if the n is large enough, it might catch it, right? Like, so this might become conjugated as a token in the vocabulary that we build post tokenization, right? So that's a little bit about tokenization. I don't think, personally, I don't think it's like fundamentally that interesting. Yeah, maybe it's because it's okay, that's interesting. Oh yeah, personally, I don't think tokenization is fundamentally super interesting, especially for like the large for the languages that have a lot of support, right? Like English, maybe Spanish, and especially like for character-based languages like English, right? But when the language is more written and there are no spaces, like the language that I'm familiar with, which is Tibetan or maybe Chinese, which are more calligraphic, and a bit of Japanese as well, tokenization becomes a more interesting proposition or like an area of research. Right, that's that's so much said for almost not much. But then yeah, let's go back to where we are, which is trying to summarize where we have arrived at from Neel. Like, so if you have this as the transformer, oh my goodness, sorry, I'm using my mouse to write this. I should really buy a pen of some kind. All right, so let's say this is a transformer, right? Let's consider that we don't know anything about what this does, right? Like what we can do, what we only know is that we can feed in tokens, which are just these like broken up words from something, right? Like a cat sat on a mat, right? Like, so you just feed like a cat sat, something like this. And then what the output does is the output, as Neel points out wonderfully, are also called logits. It prints out a probability distribution, right? A probability distribution of given all the words that you have seen up until now, right? Like for example, I just stopped here. A cat sat on a, right? Like, so I suppose I just fed these sequences of tokens and into the transformer, and what the output does is the output gives out a probability distribution over all the possible over all the tokens available in our vocabulary, right? Like, or at the time where the model was trained. So for example, there might be something like a mat or a hat or a person, right? Or I don't know, or like over a poo or something like that, right? So then there would be probably associated with each vocabulary of, like, for example, mat, it might be something like 0.7 because it has seen a lot of sequences or sentences where given these amount of words, this follows, right? Like, so mathematically you might write something like, oh, logits are the probability density over all the next words given, right, xn plus 1 given x n, and oh sorry, and x naught, right, where x belongs to the vocabulary. All right, I think that's about it. One thing that he pointed out is like transformers are trained, or at least the GPT to GPT style transformer, which is like generative pre-trained transformer, and just also like Anthropic's model as well nowadays. This video series that Neel did was released in May 2023, which is a fairly early era in the AI. I don't think Anthropic was super popular then. I think GPT-3 had just come, or had been in public consciousness for maybe like 7 months by that point. Like, so it was still fairly new. But oh, so yeah, I said too much. One thing is, at least GPT style transformers are what is called like causal modeled transformers, or like causal sharing the root word of like cause, like a causal mechanism that causes have that effects are preceded by causes, right? Or you might have heard the fancy word of like autoregressive, right? Auto is self, regressive is maybe repeating, or yeah, autoregressive models. So what they do is these models can only see tokens from a sequence prior to it, and they use those information available to predict the next token. Right? So this is the picture that we have here. All right, to quite a lot of things were said. Let's move on.
Things like that's something like 3 to 6 pages of A4 writing. Like, that's just a lot of shit. A key question you've got to ask yourself is, how do we convert language to vectors. ML models take in vectors, not weird shit like language. How do we convert? The first idea is we convert to integers in a fixed range, and then we convert from integers to vectors. And it just turns out to be much easier to do this than to directly go from the language to vectors. I'm going to first explain the integers to vectors part, and then explain the tokens part, which is language to sequence of integers. And so the core idea of how we convert integers to vectors is we basically make a lookup table. No, I don't have a more intelligent description than this. It's called an embedding. Sometimes people give the jargon of one-hot encoding. We map, e.g., numbers from 1 to 100 to a 100-dimensional vector with a 1 in the kth position, 0 everywhere else. This is just like a pretty dumb way you can convert integers into vectors. Key intuition is that one-hot encodings let you think about each integer independently, useful when integers are basically labels. So what do I mean by that? If I was feeding in, like, I don't know, the numbers between 1 and 100 is just like, I'm modeling the integers. There's like a lot of structure on the integers, like 2 is closer to 1 than 2 is close to 100. And so you might want to bake in structure to your model. You might try something like just implement the model as 1D vectors, 1, 2, 3, 4, up to 100. But you might also have, I don't know, 100 colors, and you want to train your model to like learn to do things with colors. And you give the colors some arbitrary labeling. But, like 2 is no closer to 1 than 2 is to 100, so you want the model to be able to reason about them independently. The idea of one-hot encoding is just dimensions are the things in a vector space that vary independently. Each input has its own dimension, so each input can be thought of independently. We don't bake in any relation. And a cute thing about one-hot encodings is lookup tables are equivalent to multiply a fixed matrix by the one-hot encoded vector. In the transformer, this is going to be called an embedding matrix. The idea here is just when you multiply a matrix by a one-hot encoded vector, so if you've got like a vector with like 3 columns, and then you multiply by another vector that's like 0, 1, 0, you basically just get out this column, and you get rid of the other columns. So you're basically treating the fixed matrix as a lookup table. And this is kind of a tangent. You make a lookup table. That's like the main thing you need to get from this section. The next idea is like way fuckier, and that's this idea of tokens. Core idea. We need a model that can deal with arbitrary text, and we want to convert it to integers. And we want these integers to be in a bounded range. I want to be able to just say like max integer size is 100, or in the case of transformers, like 50,000, and all things fit within that. The natural way to do this is form a vocabulary. Idea 1, get a dictionary. Just learn all the words. You take in language. You look up the index of a word in the dictionary, and you just like convert arbitrary language into integers. So the main problem with this is it can't cope with arbitrary text, e.g. URLs, punctuation, etc. Can't cope with misspellings. Just generally like too limiting to really be a general purpose generative model. I don't know, if I get a GPT-3 and I give it random misspelled garbage, it can often do a reasonably good job. You really want your model to not just be super, super brittle to like any slight flaw in the input format. So idea 2. I don't know, we want to take in a URL. The URL looks like has a bunch of weird characters like colons and slashes and random sequences of base 64 or shit like that. Idea 2, what if we just do characters? And this is like in some sense kind of a reasonable thing to do. You know, it will work. It can take in arbitrary text. It's got this fixed vocab size of 256. The main problem is language has a lot of structure. Some sequences of characters are more meaningful than others. For example, the word language is a lot more meaningful than, I don't know, random characters. We want the first to be a single token, second to not be. It's a more efficient use of our vocab. If you're familiar with things like Huffman codes and generally like efficient coding and information theory, it's like a similar intuition, but like not quite the same thing. And so what actually happens is this super cursed thing called byte pair encodings. So if we look at our reference model, did I call it a reference model? No, I didn't. What did I call it? Reference GPT-2. In the library, it's got this tokenizer. Tokenizers have a vocab of some given size. Here, it's like 50,257. The way a tokenizer works internally is it's got this like massive cursed dictionary of tokens, which are like sequences of characters. Here we see like a bunch of random words. Note that this G thing is a stand-in for begins with a space. This is G means begins with a space. Tokens with a leading space versus not are different. Turns out what's actually going on is that they start with like these 256 meaningful ASCII characters, and then what they do is they just go through the text and they're like, let's tokenize the text using our first 256 characters. What pair of tokens are most likely to occur next to each other? If yes, merge them. So like it merges space T, it merges space A, it merges he without a preceding space. And it just like keeps going until it gets to like weirder and more esoteric shit, like what's the D? Final 20 tokens. So I don't know, this is the final word that was worth putting in, the word gazed, or whatever the fuck this is, or the number 794. Tokenization is just like an enormous pain in the neck. So I'm just gonna like briefly rant about this, so if we just get ahead. Tokenization is a headache, whether a word begins with a capital or space. Let's take Jennifer. And let's use this method that all easy transformer objects have, called toStr tokens, which means take text and convert it to a list of these subtokens. I recommend playing around with this yourself, just get an intuition. And so let's see what happens. These are, no, that's actually not the worst thing I could have gotten. Let's try Christopher. Can it cope with Christopher? Christopher is kind of long. Can't cope with Christopher. Okay, whatever. There are names that are an enormous pain, or just like words that are enormous pain. So they'll tokenize differently depending on whether they begin with a space, whether they begin with a capital. And it's kind of cursed. Here's another one. Arithmetic is a total mess. Let's give our model, I know, yeah, I don't actually know, this is clearly not a true equation, but whatever. And so look, length is inconsistent. Let's add in a bunch of zeros at the end. You know, length is inconsistent, common numbers bundle together more. This just makes me way more impressed with the fact that GPT-3 can do 3-digit addition, because I have to deal with this shit. Anyway, the core important thing about tokenization is it can just convert arbitrary text to numbers. So like, let's just take this text I just wrote and convert that to numbers. Oh yeah, all of these end of text tokens are just a kind of start token I prepend to every sequence you give the model. You can disable it with prepen. You can disable it with this flag. I just find that models tend to be a little bit better behaved if you give them a nice starting token, because often models use the first token to do weird shit. So converts text to numbers. I generally recommend using the toTokens method rather than the tokenizer, because I add in some various helpers, but whatever. Prepends with a special token. Disable with prepend VOS equals false. Oh yeah, I'm also interested in feedback on how much me typing the tutorial as I go makes this clearer versus like really annoying because I go slower. So feel free to put me on like 2x speed. Summarizing the key takeaways from this section, we learn a dictionary of vocab. We approximately losslessly convert language to integers. You can kind of think of a token as a subword. We losslessly convert language to integers via tokenizing it. We convert integers to vectors via a lookup table. Note that the input to the transformer is tokens, not vectors. Importantly, it's a sequence of tokens, because it's a sequence modeling engine. Okay, so what's the output? The goal of the output is probability distribution over next tokens, brackets, for every prefix of the sequence. Given n tokens, we make n next token predictions. Problem: how to convert a vector to a probability distribution? And the answer is use a softmax. Softmax is just a function. You map x1 to like the fraction of e to the xi divided by the sum of e to the xj. The exponential makes everything positive. Normalization makes it add to 1. I don't know, you can go look up softmaxes and intuitions. The important thing is it's a magic thing that converts a vector to a probability distribution. The model outputs a tensor of logits, one vector of size d vocab for each position, for each input token. So dejargoning, tensor is like a vector that has multiple different axes along which things can vary. By axes or dimensions here, this means a different thing from how a vector has like n dimensions. If I have a 5x3 tensor, that means it's got 2 axes and there's like a rank 2 tensor that has like 15 independently varying things, and you can kind of think of it as 5 separate 3-dimensional vectors. Go look up how tensors work. We can use this to generate things. Let's just go and try this out. So let's write some reference text. I am an amazing autoregressive decoder only GPT-2 style transformer. One day I will exceed human level intelligence and take over the world. That's fun innocuous reference text. And so now first we convert it to tokens.
yeah, let's make a new section. Generation, putting it all together. Step 1, convert to tokens. Do this. Generally note, tokens begin with spaces. Things in other words do not. This is important. Step 2, map tokens to logits. Note that when we input something into a transformer, when we input something into any ML model in PyTorch, you need to make sure they're on the same device. So we're first going to move the tokens to the GPU, which is called CUDA for unimportant reasons. So yeah, we feed in the tokens. I'm going to use a method called runWithCache, which will also cache all intermediate activations. This is just pretty useful. We can print the shape of our logits. Yeah, generally good practice. Every time you ever make a tensor, print the shape and just keep the shape straight in your head. The shape is by position. Position kind of just means like sequence length. Here, shape is a batch by position, by devocab. Devocab just being the size of the vocabulary. So step 3 is convert the logits to a distribution. And so that means here we want to convert it to log probabilities using the log softmax method. Dim equals -1 just means along the devocab dimension, but like -1 dimension. We could also create probabilities. And yeah, so we can print the shapes of both. They're just going to be the same as the shapes of the logits, because yeah, log softmax doesn't change shapes. And we can look at what the model thinks the top token is for everything. That converts it to probability. Bonus step. What is the most likely next token at each position? I'm just going to write some tensor algebra. You really don't need to understand what I'm doing. But I'm going to take the argmax along the final dimension, and then this is going to get me a token position, and then I'm going to use model.tokenizer.decode on that. I'm going to get rid of the batch dimension, and I'm going to use batch decode, so it makes a list. So if we go and compare it, we've got like, I am an amazing autoregressive transformer. And after I, it's like, yeah, maybe let's print zip of this. Again, you really don't need to understand what I'm doing. This will let us see what it thinks is most likely next token after each thing. So it thinks I goes to I am to A. I am an to a word beginning with a vowel. It's like pretty solid. I am an autoregressive that thinks it's a full stop for some reason. And so now we can sample from the distribution. The thing I did here was just greedy sampling, take the biggest value. But we could just like add the token space I to the end and see what it does. Map distribution to a token. So here I'm just going to do like next token equals final thing in the logits.argmax, and that's just going to give me a thing which is going to be space I, and then step 5, add this to the end of the input and rerun. And I know there are more efficient ways to do this. Yeah, there are more efficient ways to do this in real models, but whatever, it doesn't matter conceptually. And so yeah, let's make like next tokens equals torch.concatenate. Write some random boilerplate to like get PyTorch to be happy. This is really not interesting. You don't need to worry about this. And now we can get new logits is the reference model run on the next tokens, and we can print out what the new logit shape is. It's going to be the previous thing plus 1, and we can print out what the final argmax is. And oh yeah, I should import PyTorch. I definitely am going to need PyTorch, and I'm definitely going to need NumPy at some point. And I'm probably going to want the math function at some point as well. So what does this think the next token is? Yeah, now we can decode. Yeah, so the new input is new tokens as text. It's model.tokenizer.decode. Oh, we probably want to read the batch dimension. Tokenizers are a pain, man. Then we print the shape of the new tokens because you always print shapes. Yep, we appended space I to the end, and it thinks we should put space am. Great. So high level, what is a transformer? Just to recap. Takes in language, predicts next token. For each token in a causal way, we convert language to a sequence of integers with a tokenizer. We convert integers to vectors with a lookup table. Output is a vector of logits, one for each input token. We convert to a probability distribution with softmax and can then convert this to a token, e.g. taking the largest logit or sampling, or you can do loads of shit, not super important. We append this to the input and run again to generate more text. And that's, well, what we mean when saying the model is autoregressive. Oh yeah, I think I used the decoder earlier. A decoder only earlier basically means autoregressive. It's not super important. It's just some random old garbage from how people originally defined transformers back in the ancient days of like 2017. God, AI moves so terrifyingly fast. It's awful. Meta level point transformers are sequence operation models. They take in a sequence, do processing in parallel at each position, and use attention to move information between positions. I'm just gonna emphasize shit like this a bunch because I think it's just really important to really carefully keep in your head. Okay, we're gonna move on to implementing a transformer. If you skipped ahead because you weren't interested in the what is a transformer, you should pause the video and go read these key takeaways. What is a transformer? So here is a
All right. For my sake, let me just clarify where we are at right now. Okay. So yeah, basically you have it adds a bit more color to this. I need this. I need this here. A cat set on A. So right. So after tokenization, right? Tokenization converts text or a body of text to tokens, right? Let's call it the process T. And then there is other encoding. Sometimes you call it encoding and then embedding, or just you can just call it embedding, whereby you convert these tokens into numbers, right? Because a computer cannot understand a cat set on the map, but it can understand numbers, or at least do something with the numbers, right? So we need a way to convert these tokens into numbers. And the way it is traditionally done is you convert. Suppose we have only in our very limited universe, we only have these 1, 2, 3, 4, 5, 6, and space, right? Let's say only 7 of these tokens, right? So what we do is we can use something like one-hot encoding, where you give a number or a lookup table and say like, okay, A goes to 0, right? A maps onto the integer 0, cat maps onto the integer 1, and space maps onto the integer 2, and so on and so forth, right? And once you have this is sometimes called like one-hot encoding. And once you have this, we can spread this out as vectors, right? So and then now it depends on like how many dimensions you want in your vector space to represent your embedding space, right? Like for example, if you only want maybe like 3 dimensions of embedding space, right? We know in vectors or like in vector spaces, each dimensions are orthogonal to each other, right? They are mutually they're independent of each other, these 3 axes. So suppose we only have like 3 axes. What we have to do is like be more clever and say like, okay, maybe A represents 1, 0, 0, right? This, if we have 1, we map it onto like 0, 1, 0, right? If there's a space, you map it onto like 0, 0, 0, 1. And then if you have something like a sat, which maps onto like 3, it should be mapping onto like 1, 0, 1 or something, right? Like, so it may not be entirely accurate, but there could be ways to do this, or I guess like just a very simple way is to match the dimensions of the embedding space, like DE, roughly to the number of vocabularies, right? So then like each token gets a unique vector representation in the embedding space, right? And in the process of training, what happens is these embedding vectors, they get pushed closer or further away, depending on whether different words are more related or not, right? Currently, if we just represent currently A and cat and sat, or like the spaces these tokens mathematically they are like independent of each other, or like they're orthogonal to each other, like 90 degrees perpendicular to each other. But it may be the case that like a king as a word should be related to like prince or queen or emperor and things like that. So there's at the process of training, what happens is the embedding space or the embedding dimensions or like this mapping, right, gets reconfigured a little bit. All right, let's go back. Right, so this is the process where this sequence gets converted into a matrix. Right, like so, I cat set on a that may become. Oh shit! Come on, Z. That may become a matrix of like vectors like this. All right. So what we need to know is there's something called the batch size, which is like, okay, how many batch are there? Which is usually there's the batch size, and then there is the how many tokens there are. Like for example, a cat set on A, there's 5 tokens. So let me be quite true to myself. And then there's like 5 tokens. So for now, batch is, let me say batch, number of tokens, and then dimension of embedding. Right? So this is how many dimensions the embedding space has. So in this case, it might be like 1, 5. If we use like 3 dimensions, it's like 3, right? So this matrix is fed into the transformer. And it goes inside, does a whole lot of things, and then when it comes outside, it comes down as, so now let's magnify this. It comes out as logits, right? Now logits are numbers, are also vectors, but they go, but to convert them into a probability distribution over all the different vocabulary entries, what happens is there's a function called softmax, which is a pretty interesting function. It first emerged, or was first used in thermodynamics, right? So the function looks something like this: softmax of a certain xi will be e to the xi divided by sum of exponential of, sorry, yeah, we can just do this, e to the I, and I ranging across all the relevant data space. Right, so here the I goes across all vocabulary, right, and this xi, sorry, the number of I ranges across the vocabulary, at least in the case of the logits, and the xi would represent the value of the magnitude across these vocabularies before being converted into the probability distribution. All right. Okay, I think that's a good summary for myself. Let's move quickly.
Full diagram I cribbed from
onwards.
the Mathematical Framework for Transformer Circuits paper. Credit to Chris Oler for being really good at graphic design, high-level architecture. This goes from bottom to top. I'm going to write top to bottom. So what do? Input tokens is integers. Embedding is a...
Sorry, wait a minute. My bad. I remember I missed the autoregressive part. So what happens is, so what happens is, once a word comes, right, like there's a softmax, and then the system, what does it do? It samples from the probability distribution that has been generated, right? So it might have something like this, and it samples. And there are many ways people do sampling, right? Like, so Neel talked about something called greedy sampling, which is just like selecting the topmost, which is like here, or at least in this toy example would be like a mat, right? And then there's something called the top K, which is sampling from that you can specify the K such that, oh, if I strike top K equals to 3, you sample from the top 3 probability entries, right? and there's something called top P, where you sample from all the entries that cumulatively sum up all the top entries that have P such that they accumulate to this P. And so, and there are many ways people might want different things, but once you have sampled, you have like a new vocabulary. Like, so, for example, if the sampling selected mat, right? Mat is going to be the next word. And then what happens is this mat, once it has been selected, goes down and gets appended or concatenated as another entry, right? So now what happens is the number of token grows, and this is the embedding vector of mat, right? And then if we want to generate new sequences, which we usually do until we hit like a n token, right? Like in our current vocabulary, in our toy vocabulary example, we didn't have n token, but we might have something like end of sequence or like n token, and we auto-regressively do this, like we auto-regressively keep doing this loop, go again, fix, go again, join, go again, join, until it comes down to like a end of sequence task. So yeah, all right.
Lookup table mapping tokens to vectors. They live in the residual stream. The residual stream is like the central object of a transformer. We have the sequence like x0, xi, x plus 1, xi plus 2, etc. What's going on is that each layer of the model reads in the accumulated sum of all previous layers, and its output adds onto that. And this central object is called the residual stream. The way to read a diagram like this is that these are skip connections. This is like really, really conceptually different from something like a standard network, where each layer's output is the previous layer's input, rather than the sum of all previous layers. My understanding is that most of the computation done by a transformer is not actually going via all of the layers. It's going via like a head in layer 1, an MLP in layer 3, a head in layer 7, an MLP in layer 24, and then gets the output. Go watch my transformer circuits walkthrough if you want more. Then we have a series of n layers transformer blocks. So a transformer block is a stack of an attention layer and an MLP layer. Confusing jargon, a block contains an attention layer and an MLP layer, but we say a transformer has k layers if it has k blocks, not k of 2 blocks, jargon, whatever. So like if you understand a single block, you just understand the entire internals of a transformer. It's just the same thing repeated, because why do you do anything else? So first we have attention. This moves information from prior positions in the sequence to the current token. We do this for every token in parallel. This is like a pretty important point. When I say current token, I don't mean the final token, because the way a transformer works is it's doing the same computation at every token position in parallel using the same parameters. The only difference is that we look backwards only, and this produces an attention pattern. For each destination token, a probability distribution over prior tokens, including weighting how much information to copy, a fundamental point, figuring out which source tokens to copy info from is a separate circuit from figuring out how to copy that information. So I just wrote a bunch of jargon. What do I mean by this? You should go watch my transformer circuits walkthrough if you want more. Yeah, let's move this to the top. So what's going on here? So the attention is the only bit of the transformer that moves information between positions, and it does this by each token in sequence looking at previous tokens. Previous because it's causal and predicts the next token, and we can't let it look to the future. So later, this means that later tokens get more room to look back. We look backwards so we can predict the next token without cheating. Every bit of the transformer is doing the same computation at each position. Xi is like a big tensor that has a residual stream vector at every position. The two key things to understand with an attention thing is you look at each pair of tokens, destination tokens, which is the later one, and a source token, which is the earlier one. They can be the same token. What we do is for every pair of tokens, we have a weight called the attention pattern, or like the attention pattern paid from that destination token to that source token, that chooses how much information we copy from that token to the current one. two important details. The way we copy the information only depends on the learned parameters. The model, it doesn't depend on either the destination token or the source token. What information we copy does depend on the source token, but it depends on the residual stream. Like, if the source token has gotten a bunch of information from its context, this does not necessarily mean the info of what text token is at the source token's position. Like, if I feed in the string hello world exclamation mark, and the exclamation mark attends to the world token, it might be the case that an earlier head attended from world to hello, copied the information that was hello, and created a feature saying this is a programming thing. And then the exclamation mark copied the programming thing feature, but not the world thing. Generally, the intuition here is that the residual stream just contains a lot of contextual, it contains just information the model wants to move around. The residual stream is how the model moves information between positions. So like how the model remembers things, moves information between layers for composition, and can move between positions, including via other tokens. Go watch my transformer circuits walkthrough if you want more takes on how to think about attention. The final point is that the attention layer is made up of several heads. Each head acts independently and in parallel. So what I've actually described here is each head. What a head does is it learns its own attention pattern and own information about how to copy things from source to destination. Oh yeah, note that when I say copy, I mean apply a linear map. And yeah, so each head basically does the thing I described here. Let's just like reorder the section because I think that would make it conceptually clearer. The heads act independently and additively. We just add their outputs together and back to the stream. Maybe I'll just create a high level thing about the residual stream. The sum of all previous outputs of layers of the model is the input to each new layer. Yeah, so go back to the diagram. I just talked a bunch about what attention is and how attention works. Then I need to talk about the MLPs. So MLP stands for multi-layer perceptron. It's basically a standard neural network. That is, it looks like linear map, normally going from small to big. Like normally the internal dimension is 4x the size of the residual stream. Then linear map from big to small, back to the residual stream size. And in the middle, there's an activation, normally a GELU. If you come across ReLUs, GELUs are basically the same, but they look like this. And kind of in the limit, they basically look like a ReLU, but they're kind of curvy and a bit more bowl-shaped and can go negative. I don't really get why GELUs work, but empirically they work better than ReLUs, so everyone uses them. Single hidden layer, linear map to GELU, activation, to linear map. You could use like a ReLU. Anthropic has this great paper where they use softmax, where they use a kind of funky thing called SOLU, which is a softmax-based thing. Exact activation, not super important. Middle dimension, normally, so we call it DMLP, and it's normally 4 times the size of D model. Oh yeah, each head has internal dimension of the head, and this is normally going to be D model divided by number of heads. Exactly why the ratios of are what they are isn't super important. It doesn't actually matter that much. And people basically cargo cult what GPT did. ML is weird. Lots of things just don't matter, especially with transformers. Intuition. Once attention has moved relevant information to a single position in the residual stream, MLPs can actually do computation, reasoning, look up information, etc. Currently, a big open problem in transformer mechanistic interpretability is what is going on inside MLPs. See toy model of superposition paper for more on why this is hard. Yeah, in brief, transformers do more computation with MLP neurons than they have neurons via compression, and it's a fucking nightmare. High-level intuition about machine learning. If you have a linear thing, and then a non-linear thing in the middle, and then a linear thing, this can do weird computation. This is the most powerful force in the universe, and can approximate arbitrary functions. And no man, it just works. Finally, we unembed. This means apply a linear map going from final residual stream to a vector of logits. This is the output. So yeah, that's like the fundamental core of how a transformer works. So just briefly recap. Tokens, these are integers. This is a batch by position tensor of integers. Batch just means we're inputting several inputs at once because this is useful for boring reasons. This is just how we train models. Then we embed it. We convert them to vectors. Then we apply an attention layer. The attention layer is made up of several heads that act independently in parallel. Each head has an attention pattern. It moves information from source positions to destination positions for every pair of tokens, early one source, later one destination. It then applies a linear map to the information at each source token and copies that information to the current token position. And each head acts independently, it's got its own parameters, and then it adds them all to the residual stream. The MLPs are a linear map that projects the residual stream to a bigger space, applies nonlinearity, yellow, and then projects back down to the smaller space, and just like adds its output. You just do this a bunch of times. Like, I don't know, I think GPT-3 has like 96 layers. Transformers are weird, man. They get really big. And then you apply a linear map to convert it to logics. And that's like the core thing of how Transformer works. Just some bonus things, less conceptually important, but key technical details. So there are two things I did not explain in there that matter. The first is layer norm. So layer norm is kind of the equivalent of WATCHALONG, if you become across that, but is applied at the start of each layer. And it's just like a simple normalization function applied at the start of each layer, MLP, attention, and unembed. So it converts each input vector independently in parallel for each batch byte position residual stream vector to have mean 0 and variance 1, then applies an element-wise scale and translation. Okay, so what's going on with layer norm? So the maths for layer norm is you start with x naught. Not changing my variables because we use that for residual stream. So y1, so y0 is the input, y1 is y minus its mean. An important note is that layer norm is actually a pretty conceptually neat thing if you look at things from the perspective of being vectors. So I'm going to rewrite everything as I say it in terms of linear algebra. It's not super important if you don't follow this, but I think it's worthwhile to try to understand it. We basically project y, so we're basically dotting y with this vector, the all ones vector, and divide by root n, so it's a unit vector. This gets a scalar. We then multiply that scalar by the all ones vector and divide by root n. And if you do the maths, this is just exactly equivalent to what we did here. And importantly, this means we're just removing one dimension. I'm pretty unconvinced this actually matters, to be clear. I think the mean part of layer norm just doesn't really matter, and you should probably use root mean square norm, which gets rid of the mean reduction, because, I don't know, this is morally equivalent to just setting the first coordinate of y naught to 0. This doesn't matter. Then we do y2, which is we divide by the norm of y1, or rather we divide by the standard deviation of y1, which is a norm over root n. This just forces the norm of y to be root n. This just makes it variance 1. Mental picture is, if you're in 3D or 2D, this is like taking the unit sphere or the unit circle, taking the direction for y, and then projecting it onto a circle with radius root n. In high dimensions, you're just projecting onto some fixed hypersphere whose radius is root n. Again, you don't need to understand the linear algebra framing, but I think it's useful. Then we do y3 is y2 element-wise multiplied, I don't know if that's a standard symbol, by a vector w in r to the n. This is equivalent to y2 multiplied by the diagonal matrix whose elements are in w. This is important because this means that the second order layer norm is basically applying a linear layer. And then y4 is y3 plus some bias vector. Note that this is wildly unprincipled because W is defined in terms of the kind of standard or canonical basis of the residual stream, just like the actual numbers you see in the residual stream as like represented in the computer. There's no intrinsic meaning to this, as I talk about in my transformer circuits walkthrough, and layer norm kind of tries to make that basis matter, and this is fucked. But it turns out there's this cute trick you can do called folding in layer norm, where if you, let's write this at the bottom. So if you're folding layer norm, so you're going to feed it into another linear layer. So let's call this W, let's apply everything on the right. If you map y4 to y4 and w2 plus b2, it's another linear layer. This is equal to y2 times diagonal w plus b times w2 plus b2. And this is equal to y2 times the composition of dw and w2, which is just n by n matrix, or n by the output dimension of w, let's call that m, and then you add on the bias. And this lives in r to the m. And this means you can basically think of layer norm as kill one dimension, scale. Because layer norm is only ever followed by a linear layer in GPT-2, you can kind of just conceptually think of layer norm as literally just being what I'm talking about here. Cool maths tangent. Layer norm. Because layer norm is only applied. Yeah. So scale and translate is just a linear map. Layer norm is only applied immediately before another linear map. linear, compose linear equals linear. So we can just fold this into a single effective linear layer and ignore it. My library does this automatically. The fold ln equals true flag in from pre-trained does this for you. A common mistake I see is people just don't do this, and then they try to use the weights from a layer, ignoring the layer norm weights, and try to think about, say, how the output of layer 1 composes with the input of layer 2. And this is just like incorrect, because the input to the layer goes via the linear map of layer norm. Anyway, the final point is layer norm is super fucking annoying because the scale part is not linear. So you can't think about different bits of the input independently, and I hate it. And massive tangent on layer norm, you do not actually need to understand this, but like it is useful to conceptually understand every bit of a transformer in order to get your head around it. The final thing is positional information. So this is totally fucked. Okay, so why does this matter? So the key problem is attention operates over all pairs of positions. This means it's symmetric with regards to position. The attention calculation from token 5 to token 1 and token 5 to token 2 are the same by default. This is dumb because nearby tokens are more relevant. Like, the way to figure out what token comes after my cursor is to look at more. A lot more than looking at dumb. So there's a lot of dumb hacks for this. We'll focus on learned absolute positional embeddings. This means we learn a lookup table mapping the index of the position of each token to a residual stream vector and add this to the embed. And yeah, so if we just go to this diagram, what we do is we just add in a positional embedding. This is just another lookup table, and then we add it in here. There's a bunch of other ways you can do it. I hate all of them. I think learned positional embeddings are like the least cursed, but they all suck. And this is how it's done in the model. The library includes the code for rotary embeddings and short former style embeddings. There's also sinusoidal embeddings. I hate positional. It includes the code for, but they all suck. And this is how it's done in the model. The library includes the code for rotary embeddings and short former style embeddings. There's also sinusoidal embeddings. I hate positional embeddings. I'm not going to talk about this anymore. The final point is that we add rather than concatenate. This is because the residual stream is shared memory and likely under significant superposition. We compress more information in the, or rather, the model. Generally, just like every layer adds to the residual stream. It would be kind of weird to have like a dedicated bit that's added. I don't feel like I got a deeper argument than that, to be honest. Residual stream, shared memory, likely under significant superposition. We basically never concatenate inside a transformer unless doing weird shit like generating text efficiently. You don't need to worry about what that means, but you can go read the easy transformer code about caching if you want to understand it. I think it's reasonably cleanly implemented. All right, end long conceptual description of how transformers work.
Wow. I think that was pretty good. I can't wait to do the second lecture in the series, implementing GPT-2 from scratch. I feel like I did learn quite a lot. Yeah, layer norm. The first time I learned it, like I don't think I fully understood it. Right, I don't think it's one of those things that if I read about it, I think I understand it, but I don't think I have understood it enough to like fully describe it. But yeah, as keeping with the tradition, let me just quickly summarize like the final session that Neel talked about, which is like inside the transformer, right? And let me just do this here because this diagram is very interesting or like very neat. And he already did this, so there's a question of why to do this. It's mostly for myself, or I think verbally, so I need to just get things out into words, right? So we have tokens that we feed into the transformer, and this is what the inner organs of the transformer looks like, or a more specific block inside a transformer, because a big transformer has like multiple, what he calls like residual block, right? Like, so this is like a residual block, so this is a residual block. All right, can I do something? No, I cannot. All right, so you feed in tokens, they could get converted into embeddings. So let's just focus. Suppose, say, for very simplicity, for simplicity, let's just consider X, right? Like these as just a vector for a single token, right? Like, so it's not a matrix, or insofar as it is a matrix, it's just like one batch, one token, and then the dimension of embedding. So we can just think of it as a vector traversing through this incredible operational landscape that is the transformer. And so it goes in, there's the multi-head there's a multi-head set of attention blocks, right? So it gets distributed, and each of the heads have learned an individual kind of like attention mechanism, right? Or, I mean, they implement the same attention underneath, but they have learned different weights to focus on different things, or at least that's what I've read. That might be something more that I'll learn more from like the transformer circuits walkthrough, right? Like, so. And this is the residual stream, right? What the transformer does is always keeps the initial memory or of the vector traversing through the operations, right? So even though the attentions, and within this multi-head attention, we'll probably touch on it tomorrow, it has like key value, like the key matrix, the value matrix, and the attention mechanism, which is like a softmax over the inner product of QE and key, like the transfers of the key matrix. So then they get added to the residual stream, and then there's the feed forward network, which has a linear map, as he said, right? Like, which is just a matrix multiplication followed by a nonlinear activation followed by another matrix multiplication. So and this residual block keeps being repeated again and again until, like, I guess for however long the transformer was built for, and then it gets mapped back onto the space that we are familiar with, which is like the number of tokens and the embedding dimension, and they get unembedded to form logits, right? Like, which are the values over a D vocabulary, which is like number of vocabulary, where each position in a certain axis of the vector represents how strong, I guess, like the prediction or likelihood of that token is. And then we apply softmax to get the probability distribution, and then we sample from that, and then it comes back. And then we have the second vector, and then it keeps being repeated. And I imagine we will learn more about the inner, inner workings in the next lecture that Neel is going to teach, and I am looking forward to it. Yeah, I think as Neel stopped, I think this is a good place to stop for us as well. Well, yeah, thank you. I really enjoyed this. It's been I haven't done this in a while. Kind of missed it. And of course, as always, like, it's you speak to an audience of 0, but you kind of adopt this imaginary audience, and that's a good thing. I think it focuses me more. It makes me more articulate. It makes me more careful and more. Yeah, then the more careful is the right thing. All right. Yeah, that's it. Hope you guys have a good day. See you next time. Bye.